Hello again, my dear students, and welcome to the second part for the fourth chapter dealing with noise analysis, exactly analog noise analysis. Back to our slides. If you remember, in the previous part, we have terminated our discussion on the main focus of this lecture, considering the noise associated with resistance and with transistors. Okay, so let's start with resistance. And my terminating question for this part was why we should have a noise associated with resistance. As all of us know, resistance consume or transfer electrical energy into thermal energy. So whenever a current passes through a resistance under a voltage drop, it emits some sort of heat. And this what we call under the thermal noise. So the thermal noise is mainly the noise associated with the thermal energy of or the thermal energy generated by a resistance. Thermal energy in general, not only for the resistance, is a frequency independent noise. So if you remember our previous part, when we classify noise into frequency dependent and frequency independent, and we call the thermal noise, or we call the frequency independent noise as a white noise. So thermal noise is some sort of a white noise. So whenever we have a resistance, we can remodel a resistance as a noiseless resistance associated with a voltage source that emulates the impact of the noise. This voltage source is a white source, so it has a uniform spectrum with a value of 4K TR. As you see here, we are using the single band representation. So if you use a double band representation, this 4 will turn to 2. And K here is pulse band constant. The T is the operating temperature, and the R is the value of the resistance. So using this equivalent circuit, let me say, or equivalent model, you can simulate the impact of the noise by adding this series voltage source. Let's have an example on that. So if we have a filter like this, sorry, before going into a filter, this will be in the next slide. So let's go to the second way of representation. So you can represent it as a voltage source series to a resistance, and also you can represent it as a current source with using the current equivalent. So simply the equivalent current source is equal V squared over R squared. So this will turn to 4KT over R. And as we already mentioned later on, or as we already mentioned previously, this represents a unit either in terms of voltage square per hertz or here ampere square with per hertz. We already, I think, discussed this, if you remember, when we discussed this voltage square, and when we go to the power density, the power spectral density, or the PSD, and we normalize this over hertz. So this ends to this ends to voltage square over hertz. And if it turns to be a current, as you see in this case, it will be ampere square over hertz. So this is the PSD for a resistance, either in terms of voltage or in terms of current. Okay, that's great. So whenever we have a resistance, we can replace the resistance by either this model or this model based on which one will make a simpler description for the circuit. Now let's have this example. So here we have a filter. This is a basic RC filter. So we now need to introduce the impact of the resistance or the impact of the voltage noise associated with the resistance. That's why we transfer from this model to this model. Here we have, this is R, the resistance, and we add this VR square. This represents the voltage, the noise voltage associated with the resistance. And now we deal with this process as a frequency process. So we have the PSD for this VR square. The PSD for this VR square is simply, as you already know, this represents the value of the PSD, which is, I think we already mentioned in the previous part, which is 4 KTR, as you can see. And now this power spectral density is inputted to this filter. If we consider the process from the time domain, it will be a convolution process. If we consider it from the frequency domain, so it will be a multiplication process with what we can call the transfer function of this filter. The transfer function of this filter is 1 over 1 plus SCR, which is very basic because we have a voltage divider between 1 over SC and R. And here, as you know, of course, S represents J omega. So this is the equivalent transfer function for the filter. Now, what we did is simply we multiply both functions. But in order to make it equivalent, as you know, here we are considering in terms of voltage square, or in a fake way, watt. So we have to square also the transfer function, because the transfer function is V output over VR. So we have to make it V output over VR over all squared. So the multiplication will be between 4KTR, which represents the 4KTR, which represents the input signal, which is VR squared, and the transfer function square, which is 1 over 1 plus 4 bar square R square C square F square. Here, as you can see, we just replace S with J omega and use the multiplication of the complex times the complex conjugate. So it ends up with omega square, which is 4 pi square F square times R square C square. That's why we have this variation. So in this case, we have this equation. In order to calculate the overall power due to the noise, what we can simply do in the output terminal, what we can simply do is that we can going to integrate this across the full spectrum. Again, here we are using a single side representation. So it's from 0 to infinity because we are using single side representation. And this will lead to a 10 minus 1 integration. And we can have a final analytical value of KT over C. This represents the overall power in the output side, the overall power due to the noise coming associated to the resistance R. What if we have, for example, another example here, what if we have two resistance in parallel here? So as you have a two resistance in parallel, it makes more easy to use this model, which is a resistance in parallel to a current source, rather to use this model, which is a resistance in series to a voltage source. As I told you, basically, you can use any of these two models. It depends on which model will be easier in terms of circuit analysis. So if we go here, we replace the first resistance with a resistance and current source. We replace the second resistance with the resistance and current source. We already know that the equivalent current is 4 KT over R. So we have here 4 KT over R1, and we have here 4 KT over R2. In order to express the output voltage as a noise, so first we express the current. The current equivalent, because this is a barren branch, so the current equivalent is simply the summation of the two currents. So it's IN1 plus IN2. Of course, here N represents noise. So IN1 plus IN2, which is 4 KT 1 over R1 plus 1 over R2. Voltages is simply current time the parallel equivalent of R1 and R2. So as you can see, it's 4 KT times R1 times R2, or 4 KT times R1 times R2 all squared, because of course here we are considering voltage square. So voltage square equal I square times R square. This R square is the parallel equivalent of R1 parallel with R2. So here we have already the parallel equivalent. This will end up with 4 KT R1 parallel with R2. So this is the output voltage equivalent for the noise associated with two resistance in parallel. Let's go to the second part, or the second main device we are going to consider, which is the transistor. As I told you, understanding the thermal noise or understanding actually the noise of a transistor is something very significant in order to express different type of electronic devices. Because simply, if we consider that the transistors are the building block of most of our electronic devices, knowing the know-how of the noise analysis for a transistor will or can be scaled up to understand the know-how of different electronic devices. In transistors, we have two types of noise sources. The first is simply some sort of a resistive thermal white noise. Simply, if you consider the path from the drain to the source under saturation region, so this is mainly applied to saturation region because you know that most of the application of the transistors are in the saturation region, either in the analog or the digital. That's why we are going to focus more on the saturation region. So in the saturation region, we can consider the current path of from the drain to the source, or actually the electron flow from the source to the drain. If we are considering an N-channel MOSFET, we can consider it as a resistive path, where the resistance is mainly related to the channel condition after pinch off point. So herein, we are using a typical model to what we did with our resistance. As you can see, this is the source point, and this is the drain point, and we introduce here a current flow from the source to the drain, representing a noise current due to the equivalent channel resistance seen between the source and the drain. So it's still a thermal noise. That's why we call it a MOSFET thermal noise. The value of this current is 4 kT. Again, K is Boltzmann constant, a T is temperature. And here we introduce the term gamma. And usually, whenever you are considering noise, as we mentioned, noise is a random signal that's usually comes up with some what we can call an empirical or semi-empirical parameters. So gamma is typically 2/3 whenever you are considering a low channel length device in the for a long channel length device, gamma is about 2/3. When you go to the submicron scale, so near to the hundreds of nano scale range for the channel length, this gamma turns to be 2. So you can use it 2/3 whenever the channel length is relatively large. So for example, 61 micrometer technology or similar technologies with tens or few of micrometers, you can use it 2/3. When it turns to be less than 1 micrometer, so when you go to, for example, 60 nanometer technology or 80 nanometer technology, 180 nanometer technology, these famous technologies with sub-micrometer range, so you can turn gamma to be gamma to be 2. And GM is a very famous parameter. I believe you already know. Maybe you can return back to our videos with the electronics lectures when we introduced GM, where GM was KT over Q, sorry, KT, K W over KN, W over L, VGS minus V threshold. And GM was what we call the transconductance gain, showing the variation between the output current in the drain to the input voltage in the gate. That's why GM. And GM is a very significant and fundamental term while we are studying the small circuit model for a transistor. So the equivalent noise associated with a transistor is 4 kT gamma GM. So now we can determine the voltage using the same condition. As I told you, here we are working in the saturation region. So when you are working in the saturation region, simply your resistance is the output resistance of the transistor. If you remember the IV curve of a transistor, so your resistance is the output resistance of the transistor. So here V output square equal I output square times R output square, and this will gives you an expression for the voltage associated with the noise between the source to the drain. So again, as we did for a resistance, it can be expressed either in terms of current source, as you can see, or in terms of voltage source, whenever which of them is easier for circuit implementation. Herein, we have another very famous and a very important source of error, which is the error associated with the gate oxide interfacing. So maybe I will not go deeply on the physics of this error. Maybe I have to make an of course video for that in order to go deeply into the MOS structure, metal oxide semiconductor structure, and the error associated with the variation between the or the interfacing between the semiconductors oxide and the metal. But what we can consider here from a mathematical point of view is that this type of error is a frequency dependent error. So this is the first time to see a frequency dependent error. Mostly in the previous studies, or maybe in the two cases with the resistance and with the MOSFET, we consider what we call the white noise error. Now we have a frequency dependent error. And this is a very famous one over F function, representing the frequency with an inverse function between the frequency and the error. Here, K is a coefficient. Usually, this case is on the order of 10 to the power 27 volts square per farad. C oxy is the oxide, is the capacitance due to the oxide. And again, if you return back to your solid state electronics module, you will remember the oxide signals and the capacitance associated due to the oxide and the CV curve for a MOSFET. W and L, of course, are very famous parameters, which are the width and the length of the transistor. So using this parameter, and definitely F is a frequency. So using this parameter, you can study the flicker noise of your MOSFET or of your transistor. And herein, we can see this very famous behavior for the overall noise of a transistor. As I mentioned, the 1 over F function makes that this flicker noise turns to be very, very high under the DC operation. So, because basically when I have F equals 0, this voltage turns to infinity hypothetically. So whenever you have a low frequency operation, we can say that the flicker noise dominates over the thermal noise. Once you go to a relatively high frequency, the thermal noise dominates with respect to the flicker noise. So this is how we can manage these two types of noise. And as you can see, my dear students, when you go for high clocking frequency digital electronics application, flicker noise is not so important because simply F is high and the frequency and the noise is low. However, when you are considering a low frequency analog application, you have to take care of the flicker noise. In summary, we can say that we have two terms that represents the noise. But what is interesting here, my dear students, is that these two types of noise are not linked to the same point of the transistor. So we have this noise, which is the flicker noise associated to the gate of the terminal. As I mentioned when I briefly described the source of the flicker noise due to the metal oxide semiconductor interface. So the flicker noise is usually related to the gate terminal, while the white thermal noise is between the source and the drain. So in order to make a summation between these two parameters, we have to make what we can call a transferring, either to transfer this from the source, drain source side to the gate source side, or transfer the flicker noise from the gate side to the drain side. And if you remember my words, my dear students, that GM represents the transconductance gain between the drain current and the gate voltage. So in order to return this term back, to be represented in terms of a gate voltage, what we can do is simply we can divide this by Gm square. So if we divide this term by Gm square, that means that we transfer the term to be expressed in terms of a voltage on the gate, not a current into the drain. And this is typically what we did here, as you can see. So it's 4kT gamma, and now you have Gm in the denominator, which is simply due to that we divide here by Gm square. So Gm goes with one of the Gm in the denominator, and we have here 4kT gamma over Gm. This represents the voltage on the gate, representing the white thermal noise between the source and the drain. And now we can make a direct summation with the flicker voltage as a K over C oxide, over C oxide WL times 1 over F. And of course, our unit is V square over Hertz. So this is simply how we can determine the equivalent noise on the input terminal of your device. Another one can write a similar equation in terms of the current between the source and the drain, simply by multiplying this with Gm square. So if you multiply this by Gm square, then you are now transferring the flicker noise from the gate terminal to the source and the drain terminal, and then we can have an addition with respect to this current flowing in between the source and drain. So as you can see, we can represent the noise of a transistor either in terms of gate voltage, input gate voltage, or the output drain current, which will be easier for you for representation. Now let's go to solve some examples. In the tutorial, you are going to show more and more examples dealing with the circuit, the noise analysis of different analog circuits. So this is a very standard common source amplifier that we already studied together in our electronics 1 and maybe in our electronics 2 courses. Now, what we are going to do simply is we are going to make a noise analysis to this device. The most easier way to make a noise analysis is to ground your input. When you ground your input, you make a very additional facility to study your circuit, because simply whenever the input is 0, the output should be 0. Any output recognized at the output terminal when the input is 0 is definitely due to noise. So that's why usually when we did noise analysis, we ground our inputs. Now, when we ground our input, now I use that second way. So I am representing the noise as the current flowing into the drain. So we have the white thermal noise, which is this term. So this is, let me guess, this one, this one, 4kT, and this is 2 over 3 representing gamma Gm. So this is the first term. So let me go back here. So this term, 4kT, and I substitute gamma by 2 over 3, and this is Gm. So this represents the first part of the current. Then we have the flicker current, which is the current flowing, or which is the noise due to the oxide layer, but we transfer this from being to be a voltage into the gate into a current into the drain. So we will multiply this equation with Gm squared, as you can see here. So it's K, which is a coefficient, as I mentioned, C oxy W over L 1 over F times Gm squared. So this Gm squared simply represents the transferring from the gate side to the drain side. So here, this is Gm squared. Then we have, don't forget that we have a white noise due to the resistance. So we have 4kT over RD. This represents the voltage or the white noise due to resistance we already studied here, which is 4kT over R. Now our R is RD. That's why we have RD now. So these are the 3 different currents moving in our circuit, and these 3 different currents are mainly due to three sources of noise. We have wide thermal noise due to that the MOSFET between the source and the drain. We have a flicker noise at the gate due to the metal oxide semiconductor interface, and we have also a wide thermal noise due to the resistance here. So in order to transfer this current into voltage, we have to multiply by resistance square. So this means that the output voltage due to the noise is simply the summation of all these current multiplied by RD square. So you get here RD square times all these parameters. Then you get the output thermal noise. So when you ground the input and you measure the output and you find that the output is not typically equal 0, then this output voltage is mainly due to these three sources of noise, as you can see. Now, what if we need to express the output, sorry, the noise in terms of the input, not the output? So here, this equation represents the output noise of your common source amplifier. What if we need to represent it in terms of the input voltage, not the output voltage? So it's very easy. We already know that V output over V input equal what's called the AV, or the voltage gain. So in order to represent the input voltage noise, this is simply the output voltage noise over the AV, or the gain. And if you return back, of course, here we have the gain square because I have input and output voltage square. And if you remember, the gain of this amplifier was negative GM RD, if you remember. So the gain square is GM square RD square. So simply, if we divide this with GM square RD square, you will get this, which represents the equivalent input noise due to the three sources of noise we have. So this shows you how we can make a full analysis for a common source circuit in terms of an analog noise analysis, and how we can predict the output voltage noise and the input voltage noise. Let's go to another example, which is again a very famous example representing two MOSFETs, M1 and M2. And again, we need to represent the overall voltage with respect to this structure. So let's see how we are going to manage it. So in order to proceed, let's go with the same way. So each of these two transistors, here calculate the input referred thermal noise. So in this question, it's mainly concerned about the thermal noise. He specified that we need only to consider the thermal noise. Of course, this happens usually, as I told you, when you are working with relatively high frequency. So whenever you go, for example, in order to analyze the noise associated with logic gates, for example. So with logic gates, you have somehow relatively high clock. That's why we can go to this portion of the graph. So whereas relatively high frequency, you can say that, okay, that thermal noise is dominating. So in this question, it's specified that we are only concerned about the thermal noise. So what we are going to do simply is just we are going to add the thermal noise of our transistor. So simply the thermal noise, if you remember, my dear students, the thermal noise here, yes, this one is 4kT gamma GM. So we are going to add 4kT gamma GM1 and GM2 because we have two transistors, as you can see here. So we have this current one and this current two, and the output resistance. Of course, we have also two output resistance. Our output one, which is the resistance due to the first transistor, is parallel to the R output 2, which is the resistance due to the second transistor. So in general, we can say that 4kT 2/3, which is gamma, GM1 and GM2, which is the two transistors. And in order to turn it into voltage, so we multiplied by the output resistance of the two transistors, R output 1 and R output 2. So this represents the overall output noise recognized at this terminal, at the output terminal. If we would like to return it back or transfer it back to the input terminal, then we have to divide this over the gain. Our gain here, so the input here is associated with M1. So the gain here is GM1, R output 1 parallel with R output 2. So if you divide this with GM1 square, R output 1 times R parallel with R output 2 all square, then you are going to get this. Of course, this will be cancelled with this, and you will have this expression representing the overall noise from the input terminal. So referring from the output to the input is very simple. Just divide over AV. Just take care. But in the noise model, when we transfer from a current to a voltage, from the current in the output to the voltage in the input. That's why we use the term GM square. So if I'm transferring the drain current into a gate voltage, I will divide by GM square. If I transfer a gate voltage into a drain current, I will multiply by GM square. While in the circuits, when we transfer from the output to the input, here is output voltage and here is the input voltage. So we use AV. So we divide by AV or the gain due to the amplification stage. That's why here we divide by AV square, not GM square. So take care of that. My final remark in this video is, now we did what we call a noise analysis for our circuit. But is it possible to control noise, or noise is uncontrollable parameter? Actually, what we have recognized together is that noise is a controllable parameter. This is the expression we reached together. So this is simply this expression. The expression we reached together. So, I'm sorry. If we go to this expression, you find that the equivalent noise on the input terminal is function of GM, strong function of GM, RD. And if you go to the flicker noise, you will find that this is function of oxide capacitance, W and L. So that means that you, as a designer, have the capability to control the noise. For example, when you have a relatively high GM, this will directly impact the white noise level. So the higher GM, the lower the noise level. The higher the RD, which is the equivalent drain resistance, the lower the noise level, the white noise level. So now you can control the noise with controlling this parameter. And of course, GM is a controllable parameter. It depends on the device parameter, W over L, K dash, and depends on the threshold voltage, and depends on the gate voltage. So for example, when we go with ultra low threshold voltage application, typically used in sensing application, for example. So when we have V threshold small, that means that you can operate with a VG small. That makes that okay. This is something good in terms of the sensing application, but this will lead to a very low GM, which means a high level of noise. So that's why maybe this appears for you when we are considering an ultra low threshold voltage transistors. In these transistors, we should expect a high white noise. Alternatively, when you go to our gaining stages with high GM, then you should expect a relatively low threshold, relatively low noise. For the flicker noise, you can control it with C-oxy, which is a very tricky parameter because simply C-oxy is also depend on W and L. So you can control, but you have to take care that GM is depend on W over L, while the flicker voltage depends on W times L. So you can increase W over L while maintaining W over L ratio the same. But of course, this is also not so easy to be controlled because, as you know, while proceeding into technology, we are aiming with smaller transistors. A smaller transistors, that means it's a lower value for W times L. It can be the same ratio W over L, but it's typically a lower value for W times L. And accordingly, you should expect a higher flicker noise. So, for example, if I compare two transistors, one was old technologies like 61 micrometer technology with another one with 45 nanometer technology, I should expect a flicker noise higher when I go with the more modern technology with a 45 nanometer technology transistor. And that's why it's a trade-off between shrinking down the transistor dimension and increasing the flicker noise. But in principle, designers are always asked to decrease the voltage, the noise associated with voltage, and that's why we call it increase the circuit immunity toward noise. So when you read the term circuit immunity, or sorry, noise immunity, it means simply to what extent this circuit have a low level of noise when we consider different types or different sources of noise. So this was the end of our lecture today, considering the noise analysis for analog circuits. In the next lecture, inshallah, we are going to start a new journey with analog to digital converters, or ADCs. Thank you very much, and looking forward to a new chapter.